to answer this question, we need to remember what a power function is. A power function is any function that looks like y equals a times x to the n. This number a can be any number except it cannot equal 0. And for the power cannot be a variable, so no variables allowed as a power. And also, this value cannot equal 0. So that's basically all we need for a power function. So looking at what we have here, we should be able to identify both a power and a constant of variation. In the case of the first question, it looks like we have a variable in the power. So we're going to say that for that reason, this is not a power function. In the second case, it is a power function, and we can identify both things that we need. Note that the power is 2, and the constant of variation, that's the number in front. So I'm just going to abbreviate COV. So the constant of variation is -1/2. In the third case, this is also a power function as well. In that case, the power is 5. And when we look at what the constant of variation is, remember that pi is about 3.14. So 5 times pi is also going to be a decimal value. That's going to end up being about 15 point something. So when we see 5 pi represents a number, represents 15 point something. So this number in front, 5 pi, is going to be our constant of variation. So our constant of variation is going to be 5 pi. So from what we just said, both 4, 5, and 6, they're all going to be power functions. So for us to get an idea of what these look like, we need to remember what the parent functions look like. Anytime we have an odd power, we note that we're going to have a piece here and a piece here. So a piece in opposing quadrants, or we're going to have either a piece here and a piece here. So either of these could be what we can have for an odd function. So how we know which one it is based on the number in front. So if that coefficient is a positive number, then that's like asking the question, are you positive? Then this thing is going to raise its hand. So the raised hand is going to be on the positive side or the right side of the graph. If, however, we have something like y equals -7x to the third, notice that when we ask the question, are you negative, it's going to be raised on the negative side. So this would go with something of that nature, with a graph of that kind. So because we have a positive value in the front as our coefficient, we know that where our ends would go. The raised portion would be in quadrant 1, and the part going down would be in a separate quadrant. Our graph would look something like this. If we were talking about the symmetry here is through this point. So anytime we have an odd function, we're going to have what's called point symmetry for our power function. So because we have a 3 here, we're going to say that we have point symmetry and when we talk about the other portions of it, the power is going to be 3 and the constant of variation is 5. For our end behavior, we're really asking what's happening when we go to the right or when we go to the left. So notice on the right-hand side of the graph, it's going up. So what we're going to say is as we go to the right, so that's what this means, as we go to the right, our function is going to go up. So basically going to positive infinity on the function means that it's going up. So we're also going to say that as we go to the left, which is the negative side, so when we go over to this side, notice that the function is going down this time. So we're going to say our function is going down. So we can do the same type of analysis on the other two functions. So for question 5, we're going to say that it is going to have a power of 4. So question 5 is going to have a power of 4. It's going to have a constant of variation of -4. That's the number in front. And we can also say that since it has an even power, that instead of having point symmetry, it's going to have what's called line symmetry. So anytime we have an even power for our power function, we're going to have line symmetry. So if we did a sketch just to see what this looked like, our even function, our even power, means that the ends are going to be exactly the same. So either the ends are both down or the ends are both up. And the way we can tell which one it is by looking at the number in front. If this number is positive, that means that both ends are up. But if this number is negative, it means that both ends are down. So notice that we have a negative value here, which means that we're going to have something like this where the ends are down. So our graph is going to look something like that. So what that means is that we have line symmetry. In fact, this time the line is right here. So we can fold along that line and it would be symmetric. So in terms of our end behavior, we can say as we go to the right, looks like our function is going down. So as we go to the right, our function is going down. And as we go to the left or the negative side, so as we go this way, our function is going down. So our function is going down. For our final question on these set of 3 problems, if we were to sketch this one, it would look very similar to the first one because notice that they both have odd powers. So we expect that there's going to be a piece over here and a piece over here, especially considering that this is a positive number. But the thing is that when we're dealing with a negative power, it changes the pieces a little bit. Instead of having them be connected like in question 4, they're going to be separated like this. So you have a piece here and a piece here. So that happens anytime we have a negative power. So what can we say about this information? Well, on question 6, we know that the power is -3. We know that the constant of variation is 3. That's the number in front. Because we have because we have an odd power, we know that it's going to be point symmetry. So any odd power on our power function is going to give us point symmetry. And we know also that our end behavior is a little bit different. It's this time when we go to the right, our function is getting closer to 0. And when we go to the left, our function is getting closer to 0. So we're going to say that as x goes to the right, as we go to the right, our function is getting closer to 0. And as we go to the left, our function is also getting close to 0. In order for us to graph this, first of all, think about what if we took away that plus 6? What if it were just x to the third power? What would that graph look like? Well, what we said on the previous slide was that x to the third is going to have n's doing different things. Because of that odd power, the n's are doing something different. So in this case, positive number 1 in front. So hands up on the positive side. That means the other side is going down. So what we learned in Algebra 2 was that if we do this plus 6 first, that means that we're going to have a transformation. Specifically, we're moving it, and we're moving it left or right. So this plus 6 affecting this x, it actually looks like it's moving it to the right, but it's actually moving it to the left. So we're moving our whole graph to the left 6. So if we take this graph, this green graph on the right hand side, and we move it 6 to the left, think about what that would look like. That means that this point that crosses right here, instead of crossing at 0, it would cross at 1, 2, 3, 4, 5, 6. It would cross right here. So if we just sketched it, it would basically be this graph. So what we have to remember here in doing this is a few things. One, the leading term tells us what the ends look like. So if we have a positive number here, or a certain power here is going to influence what happens. For example, let's say we had 3x squared, and we thought about what the ends would look like. Well, we have an even power, so that means that the ends are going to be doing the same. Either they're both up or they're both down. We have a positive coefficient, so that would tell us that this is what the ends would look like. If we changed it to be negative, then the ends would look like this. So negative 3x squared would have our ends at the bottom, whereas positive 3x squared would have the ends at the top. So what if we had something that was odd though? We have to remember that if it's odd, so as an example, if we had 5x to the third, then the fact that we have an odd number here as the power means that the ends are doing something different. So either the ends are as I've drawn them there or this way, but the ends are doing something different if this is an odd number. If this is positive, if the coefficient is positive, that means that we're going to have the raised side be on the positive side of the x-axis. So in this case, 5x cubed would have ends that look like this. And if we made it negative 7x cubed, it would have something that looks like that, because the negative says the negative side would be raised. So if we continued, first here, let's find the leading term. So to find the leading term, we take the variable parts and we're going to multiply them. So for this first x here, notice that the power is 1. So we're going to say x to the first power. For the second x that we have here, the power is 4. So we're going to multiply by x to the fourth. When you multiply and the bases are the same, you add the powers. So this is going to end up being x to the fifth power. This is our leading term. So our leading term, notice, has an odd power. So if it's an odd power, remember we said one of two things is going to happen. The ends are doing something different in one pattern or another. So to figure out which one it is, look at the number in front. In this case, it's a positive 1. So that positive 1 tells us that the raised side will be on the positive part. So this is what the ends should look like. So if we know what the ends look like, that helps us to do the graph. So let's go ahead and next step, we're going to put in the ends. So we know one end is going to be up here somewhere and another end is going to be over here somewhere. Now let's find the roots. So to find the roots, we're basically asking what's going to make this 0. So if I asked you what minus 1 equals 0, what would it be? Well, clearly it's 1. So when you see x minus 1, you know that the root, or 0, is going to be 1. What about x plus 3? So if you have x plus 3 equals 0, what would the root be? Well, clearly, negative 3 would work. So that means the root here is going to be negative 3. So let's summarize that information. So we know so far that we have one root is going to be a positive 1, and that's coming from the x minus 1. Another root is going to be negative 3, and that's coming from the x plus 3. In terms of the powers, this root has a power of 1. So in other words, we have a root of 1 with a multiplicity of 1. This root has a power of 4. So in other words, we're going to say that this 3 has a multiplicity of 4. We have to remember that for an odd multiplicity, it's going to cross through the root or go through the root. So what we expect to happen when we graph it is that because this is an odd power or multiplicity, that means when we reach this 1, that we are going to go through the graph. For an even multiplicity or power, what happens is that it's going to bounce. In other words, it's not going to cross over the graph. So what else do we need to know? We also need to find the Y-intercept. For the Y-intercept, we're going to say x is always 0. We're going to make x 0. So if we substitute 0 here and 0 here, we're basically saying 0 minus 1 and 0 plus 3 to the 4th power. 0 minus 1 is negative 1. 0 plus 3 is 3. If we have 3 to the 4th power, that's basically 3 times 3, that's 27, times another 3. 3 times 3 is 9, times another 3 is 27, times another 3 is 81. So 3 to the 4th power is 81. We still have to multiply by negative 1, so that tells us our y-intercept is going to happen at negative 81. So our point would be 0, negative 81 for the y-intercept. We now have enough information to start graphing. So let's plot these points. We said one of the roots was at 1, so we put a point at 1. Another root was at negative 3, so we put a point at negative 3. Another root was at 0, negative 81, so we put a point there. And each of these points represent stops that we have to make when we make the graph. So we start at one of the ends and we connect it. So now we're at negative 3. But remember, we said that at negative 3 it should bounce because of the fact that we have an even power. So it's going to bounce. And we have to hit our next stop, which is the y-intercept. We are going to keep going from there And now we know we're going to hit the next root, or 0, which this time is at positive 1. At positive 1, we said that it should go through our x-axis. So it's going to go through the x-axis and just keep going. And notice that the ends are exactly where we said that they would be. So one end here and another end in this quadrant. So that's how we would make the graph. As we find the zeros of this polynomial and the multiplicity, that's actually fairly easy. What we do is we look at the factor. In the case of x plus 1, negative 1 would make it 0. So negative 1 is the root. And the multiplicity is the power. So the power is 3. So that's what we'd have for the first root and multiplicity. For our next root, it will be a positive 7. And notice that the power is 1 here, so we have a multiplicity of 1. For the next root, notice that we're not adding or subtracting this time. So what we're going to have in these cases is 0. So 0 is our root, and notice that 2 is the power, so 0 with a multiplicity of 2. We could go through the same process on the rest of these. So on the next question, we'll notice that for x minus 8, 8 is the root, and 3 is the power, or multiplicity. On the next one, negative 8 is the root, and 2 is the multiplicity. But notice what happens here. That this time, this 4 doesn't even have an x, so there's no root associated with it. Concerning the rest of this, you can pause it and try and see if you can come up with it, but this is basically what it's going to do. We would have on the next one, 1 with a multiplicity of 1, as well as negative 3 with a multiplicity of 2. Here we would have negative 12 with a multiplicity of 1, 6 with a multiplicity of 1, and this 4x, since it doesn't have addition or subtraction, would have 0 with a multiplicity. This time the power is 1, so we'd have a multiplicity of 1.